Okay, we should be all good. Let me just check. Yeah, we're all good. Okay, let's get into it then. So, what were we doing last time? We finished off with function templates. Um, yeah, function templates. Um, so, we wrote last time about function templates with multiple types. And we learned that the syntax for um, function templates is uh, template type name, uh, and then usually you use T, and then you do the void, and then in the parameter you use the type name T. And you can choose to use this if you wish, but you can also not use it. But if you don't use it, uh, and we go from a different integral type, i.e., from an integer to a double, something like uh, a new function or a new template will essentially be created. Okay. Yeah. So let's go to my function templates with multiple template types. We wrote a function template to calculate max 2 values. Let's actually just write it ourselves just to get into the swing of things. So we use the preprocessor include, we use the header of input output stream. We will then do the template keyword with type name T and T max with TX and TY. And in the body, we will be doing return if X is less than Y. Then we will return Y, else we will return X. And then in our return type integer function, we will return, we will call max by a standing character output. And then we will do max, and we'll do 1, 2, and then a line break. And then again, we'll call max, and then we'll do 1.2, 3.4. And then we'll return 0. And then we'll run this. And as you can see, we get the Y versions because Y is greater than X. Okay. And this will instantiate max int, and this will instantiate max double. Cool. So here we have a template, same thing. But this time we'll get a compile error. Enough. Because we are making function call without the angle brackets, the compiler will check to see non-template match. Next, the compiler will see, excuse me, So let's just do that. So you can see there's no matching function. So we would, I assume, just need to do this. Would that still produce an error? Yeah, it still would. So you got a double versus an int. So the first solution is to use static cast. I'll just do that. And then I'll do that. And then I'll do that. So the first solution is to use static cast like we've used previously before and many times before. So we should be used to using static cast in your code. So now what we'll do is we'll close this in at least 3 ways. These ways being static cast, type, expression, providing an explicit type template argument, and yeah, and this one, function templates with multiple template type params. So first one will be static cast like we've used previously before. Using static cast to convert arguments to matching types. So this should, he says, be relatively straightforward. Okay, so let's just do it in the function then. So we'll do max. We don't need to change anything else. We just simply need to do, we'll convert the 3 to a double instead. Static cast double, because remember, different integral types can be promoted via numeric conversion. Yeah, it can be promoted. So like an integer can be promoted to a double. An integer, well, an integer is the minimum. An integer can be converted to a long, a float, a double, or a long float. So double, and then the one we want to change, the expression will be 2. So we run this, and we get 2. Good. So to prevent compile time errors, we can use static cast type expression like this. Yeah, that makes sense. Converts our int to a double. Okay. Providing explicit type template argument. If we had written the is true. I'm not going to copy this function. I'm going to copy this function, not type it out, because that makes sense to me. However, when the compiler if it won't do any type of function. So we've then converted max itself to a double. Because remember, the compiler can essentially deduce what we're trying to get at. So we can then, instead of doing static cast double 2, we can simply do the type we want. And let's get rid of that. And let's move that there. And we should, yeah, cool. So if I did type of type def, would that be a double? No, type. Cool. Because we've explicitly stated T should be a double, the compiler won't use template argument deduction. Yes. And we don't have to use static cast, therefore making it easier to read for us and anyone who wants to use a program in the future. So this okay. And I assume the next one will be easier, even easier to use. Function templates with multiple parameter types. Template multiple parameter types. Yeah, you can see already it resolves the double issue. So we're gonna copy and paste that. We're gonna do this. We're gonna move that there. The root of the problem is that we only defined a single type and then specified both parameters for the same type. The best way to solve this problem is to rewrite our function template in such a way that the parameters can resolve of different types, rather than using the same parameter such as t. We can use t and u. Okay, so let's do that. So we'll use a preprocessor of, and then include, and then the input output stream. Then we will do template, and we will do t, or type names rather, t, and then again type name u. Then we will do t max, and t will be x, and u will be y. And then the body again will simply return if x is less than y, then we will return y, else we will always return x. And then in our main function, we can simply get rid of that double crocodile bracket. So max, and then we can do 2 and 3.5. And then that, and then return 0 as always. And then we run that, and we should hopefully get 3.5. We get 3. Okay, so it actually some narrowing happens. And this is where we can use auto. So we're using 2 template type parameters. Yeah, that's fine. X can resolve to type T and Y to U. That's fine. This will result in narrowing, i.e. 3.5 will go to 3. But this resolves the int double issue. Yes, that makes sense. Because T and U are independent, they can resolve each other with no issues whatsoever. Okay. This is because the conditional operator, i.e. or this, requires the operands to be the same common type that we learn in this one here. So to fix the issue of narrowing, we will use the auto return type keyword to let the compiler deduce what return statement should be used. And then I'll just copy that there. So we remove the T and simply replace it with auto. So now hopefully when we run this, we should in our terminal get 3.5. Because that is what auto will do. And then we get 3.5. Cool, nice. Okay, so then we move on to abbreviated function types. I think I'm going to skip that now. Function templates may be overloaded. Okay. So remember in the previous streams, we have actually learned about function overloading. Yeah, function overloading. So function template, which is the idea that your function you can have multiple functions of the same name, and the return type does not define the overloaded function, but rather the actual parameters define the the overloaded function is different. So and then copy this. And then we'll do it ourselves. So the preprocessor include the header of input output stream. So we want to add two values with matching types. So we'll do template. We'll do a type name of T, and then we'll do auto add T X T Y, and we will simply return X plus Y. Add two values with non-matching types. So we'll do template type name T, type name U. We'll do auto because then the compiler will deduce what figure we need to use. Then we will do Then we will do auto add, and we will do t being x and u being y, and then we will return simply x plus y. And then we're going to adding 3 values of any type. So we'll do template, type name t, type name u, and then finally type name z. And again we'll do auto, t will be x, u will be y, and that should be capital. T will be x, u will be y, and I forgot to add the function name, and then v will be we'll just follow along. V will be z, and then we'll simply return x plus y plus z. And I'm getting an error here. Why is that? No, that's fine. Then in our return main function, we will instantiate all these calls. And I'm just going to copy this. And we should then therefore get this plus this, this plus this. Yeah, cool. So for example, if we did 2, it wouldn't work. No, it would work. That is because what if we did? That still works. Okay. Okay, so that was function templates with multiple template types. Cool, nice. So now we'll move on to non-template type parameters. Okay, next. So non-template type parameters. How are we looking on the progress? Okay, so we could potentially finish it today, depending on how long this is. So it's not too bad. So non-template type parameters. I am just going to take a quick break here and I'll be back in a second. Okay. Let's continue then, shall we? All right. So good. So good. Yeah. Okay. So where were we? Um, non-type template parameters. So non-type parameter is a template parameter with a fixed type that serves as a placeholder for a constant expression value passed as a template argument. So a non-template argument following. So you got an integral type, an enum type, a standard null pointer type, a floating point, a pointer or a reference to an object, a pointer or a reference to a function, a pointer or a reference to a member function, a literal class. Okay, we saw our first example of a non-type when we discussed bit set. Okay, defining our own non-type template parameters. Okay. Here is an example of a function that uses a non-type template param. So let's go in here. We'll do the preprocessor, the input-output stream. So template int n. So we declare a non-type template param of type int named n, which was, out of all of them, is an integral type. So we do void print, and then in the block we will do standard character output n, and then a line break. So then use m here, and then in our integer return type main function, we call print or instantiate print, and then we need to provide a type, as you can see here, of 5, and then this will print 5 as our non-type template argument. Interesting. Yeah, 5. Okay, so oh no, wrong one. Okay, so that's an interesting piece of syntax. So you essentially create, because it's a non-template type, I assume that means you then have to, that's why you need to create the type. We are defining a non-type template parameter named n that will be the placeholder for a value of int inside the print function. On line 11, we need to instantiate it. And I'll just copy what the compiler would do. So the best practice is to use n as the name of a int non-type param. So what are non-type templates useful for? No, wrong one. Press Control C instead of Control V. Control V. And then this. Cool. So function parameters as of C++ 20, function params cannot be constant expressions. This is true for normal functions, constant expression functions. Cool. So let's say we were to do something like this. The preprocessor include, and we do C assert for assert, and then include C maths for standard square root, and then include input output stream. Then we do the return type of double, and we get square root, and then we pass in a parameter of double, and then assert if d is less than or equal to 0.0, and then the message we want to apply with get square root d must not be a negative, must not be a negative number. That's fine, I'm happy with that. The assert will probably be compiled out in non-debug, in non-debug builds. So then if D is greater than or equal to, and that should be, yeah, that should be great. So D must be greater than or equal to, otherwise we get an assert message. If D is greater than or equal to 0, then we simply return standard square root of D. And then we'll return 0.0 because our return type must be a double. And then in our int main function, we will, I'll just copy and paste these because it'll be quicker and easier. Yeah, cool. So we should get 5, and then we should get error. Yeah, see, there we go. So assertion failed. It must be a non-negative number. And then we see the function that's causing the error, the file, and the line, and where to go. So it'll be line 7. When run, the call on will runtime assert out. However, static cast requires a constant expression. However, if we change the function parameter type to a non-template type parameter, we can then do exactly what we want. So this is simply changing adding a template and then a non-template type param to fix this issue. So we can then get rid of assert, and then above this we can do template, and then we'll do a double of D, and then we can remove this, and we can do static assert. Actually, we can just do this instead. Static assert. Then if, then const expression. Then here we need to pass in, because it's a non-type, parameter, we therefore need to use type names when instantiating it. So we do that, and we do that, and then we change this to the type, and this to the type, and then run it. No, we still get errors. So what am I doing wrong here? Get square root. That's all good. Oh, because the D needs to be the type as well. The non-type uh, the non-type parameter. Still getting errors. Ma perché? Is it because we need a cert? No matching for get square root. Uh, uh, because we need to remove the parameter. Got it. No. D. Double D. Double get square root. Oh, that will fail to compile. So that means we actually need to. I just want to make a note of this. This version will fail to compile. So we need this essentially. So we remove the parameters here and the template and essentially have an empty type template parameter. Then get square root will be 5. Static assert if, sorry, -5. Minus 5.0. So if constant expression minus 5.0 and then minus 5.0 and then we need to remove this. Is that the issue then? Without get square root? So template double get square root, static assert, um, static assert greater than or equal to 0 if constant expression minus what? Is it because we need to remove this? Get square root is undefined. Uh, get square root is not a template. No, that's what the my bad. This is what the compiler essentially does. So we can ignore that. And we can go back to our we can go back to this, right? Yeah, producing the error like we had. Okay, cool. Implicit Okay, we can do this. So implicit conversions for non-type template arguments. Certain non-type template arguments can be implicitly converted in order to match a non-type template parameter from different types. For example, so for example, so non-type template types, if it wasn't already hard enough. Okay, so get rid of this. Preprocessor include input output stream template, non-type template of int with n. Then we do void print. Then we do standard character output, and we'll be printing n with a line break. Int non-type template param. Int main return function print, and remember we need to create the the type now, and then call the function, and then we print, and we can do C. Why is that not? Why is that not the exact same? Template int n. Because it's double. My bad. And there we go, we get 5 and 99. I just want to clear the terminal and print it again, just to make it obvious. Okay, we get 5 and we get 99. So this will print 5 and 99 as C car will be converted to an int via ASCII. Oh, nice. That makes sense. And we've already covered these sort of things. Yes. Unlike normal functions, the algorithm for matching function template calls is not sophisticated. And certain matches are prioritized over other based on the type of conversion required. This means that this means that if a function template is overloaded for different kinds of non-type template parameters, it can be very easy to create an unambiguous match. So we got the exact same. Now we have a char, and then we're creating a char. Yeah, I can see that. because you have a non-type here with an int, then you have a non-type char, and we know that chars are essentially integral types. So this creates an ambiguous match. Okay, that makes sense. So next we'll move on to the next section. Type deduction for non-type template parameters using auto. Okay. So as of C++17, we now know that non-type template params may also use auto as the return type. No, as may use auto to have the compiler deduce the non-type template param for the template argument. I didn't actually know that. I was thinking of the return type. So non-type template parameters. Yeah. So such as this. So we'll use again the preprocessor of include with our input output stream. We'll do a template. We will have auto n, and we will do void print, and then in our block we will do standard character output n, and then because we are using a non-type template in our block, in our main function, we need to return when instantiating it. We need to what do we need to do? We need to instantiate it with a type. So we do print. As you can see here, we need to put something in, so we do 5, and then we can do empty, and then print again, and this time we can do C. And then this should deduce that we want 5 and C, rather than when we head here with int, i.e. specifying the exact return type or the exact type that we want. So this will produce the following output. So we get 5 and C. Cool. So write a constant expression function template with a non-type parameter, non-type template function, non-type template parameter that returns a factorial of the template argument. The following program should be should fail to compile if it reaches factorial minus 3. Okay, so we're going to need assert. So we're going to need include assert, C assert, for assert. We're going to need include C math for factorial. And then we're going to need, obviously, include input output stream. So we'll do a template. So write a constant expression function with a non-type template. So we'll do auto, because we may want to use doubles. We'll do auto n, and then we will do void print assert if d or if n is equal to minus 3, factorial cannot be negative 3. That's the assert. So then we leave the main as normal. So static assert. Oh no, we're going to need factorial. The only thing is we need to write the factorial. Factorial 0 equals 1. Auto. No, so we're going to make that an int. We're going to make that we're going to also make this an int. But did he say a non-int type template? No, he just said that. So int factorial. Then if we do if const expression n is greater than or equal to 0, then we return standard, I don't know what the, I don't know what, if we just click on C math, so no, not power. What would be factorial then? Because I was normally, you would use, in maths, you would use a, what do you call it? An exclamation mark. But exclamation mark in coding means not. I think I'm going to have to have a look at the answer here, the solution. So, static assert, template int end, oh, constant expression int factorial. We need a for loop. Okay, I never would have thought of that. So static assert, static assert n greater than or equal to 0. Then we'll do int product 1, and then a for loop. So for int I, starting off at 2, and that should be a semicolon. Then we want to loop through if I is less than or equal to n, then we want to add to I. And then we want to do product times I. And then outside our for loop, we want to return product. And then we'll bring those in. And it does fail to compile. Just to make sure it actually works. Does this work? It doesn't actually print anything though. This. So it's compiled, but it's not actually printed anything because it's obvious we have not used static character output. Okay. So using a for loop for to calculate the factorial value. And why is my static assert all of a sudden playing up? Okay, it's because of that. That's fine. Okay, so up next is going to be there you go. Cool. Up next is going to be using function templates in multiple files. I presume he means headers. And I believe this is our last one before the quiz. Yeah, it should be. Okay, so I'm going to take a quick break here and I'll be back in a minute. Okay. Right. Let's continue, shall we? Right. So using templates in multiple files. Okay. All right. Nice. So, uh, yeah. So instead of the following program, which doesn't work correctly, so we have a main CPP, we have a input output stream, we have a template type named T. T is adding one and is not actually returning anything. So this is essentially a forward declaration. Yes. And then we're calling said forward declaration here, but there is no definition. We got add CPP. This is the definition. We got a typelate temp T. We got a T add one return x plus one. So this is not working because we don't have a header for anything to call. If add one were non-type or a non-template function, this program will be fine. Yes. Yes. Exactly. So we need a header. That makes sense. Most conventional way is to add a header with obviously um, if not defined, and then your name macroprocessor. If not defined macroprocessor, then define, and then the thing you want to define, and then you do end if like that. And then you need to remember to use the preprocessor of include in your main CPP. Yeah, that makes sense. Yeah, it makes sense. Okay. Uh, the best practice when it comes to um, function templates in different files is to define the function in the header as always, and then use the preprocessor of include wherever needed. This therefore allows the compiler to see the full template definition and instantiate the template when needed. Cool. Okay. How's the quiz looking? Okay, why not? So we'll probably go for another half an hour and see where we are after that. Okay. Yeah, they have been complex, but they are powerful. So we'll see a lot more of templates in future functions, in future chapters. So function overloading allows us to create multiple functions with the same name, but obviously we need different return types. Such a function is overloaded. It's called an overloaded function. Return types are not considered for differentiation. Yes, we know that now. When resolving overloaded functions, if an exact match is not found, the compiler will go through those 6 steps that we did in the previous stream to find a resolution. An ambiguous match occurs when the compiler finds 2 or more functions that can match but can't determine which. A default argument, remember using equals, is a default argument provided for a function parameter. Parameters with default arguments must always be the rightmost, i.e. towards the end of the parameter. And remember, normal functions can use default arguments, and template functions can also use default arguments. Function templates allow us to create function-like definition that serves as a pattern for creating related functions. We use type template parameters as placeholders. The syntax tells the compiler we're defining and what we want to use. The process of creating functions is called function template instantiation for short, or instantiation for short. When this happens due to a function call, it's called implicit, and an instantiated function called okay, good. So template argument deduction is when, as previously said, is when the function, or rather the compiler, deduces it for us. And we can remember also use auto to allow the compiler to determine or to deduce for itself. Okay. Yeah, the auto keyword, exactly. And then a non-type template parameter is a template parameter with a fixed type that serves as a placeholder for constant expression values passed in as a template argument. Okay. So, what is the output of this program and why? So we have a void function of printing integer, and then we're just doing an output. Then we have a void print double x. So here we have function overloading, and this is key because despite the fact that they're both void, and have those same turn types, remember that the return types does not determine the function definition and the function overload. So we have a different parameter here and a different parameter here, i.e. passing in different arguments. So we're getting a short 5. So this will print, we're creating a short integer and we're creating its 5. So this will just print 5 surely because short is a integral type, so that will be converted to an integer, and we have an integer parameter here. But even if we didn't, that would then be converted to a double, or promoted rather to a double. So I assume this would just be 5. Yeah. Yeah, cool. So why won't the following compile? So we got a void print with no arguments, no parameters rather. Then we have a void print of a integer x equals 0, so we have a default type. Then we have a print double. So why won't the following compile? The following will not compile. This will compile, but this won't because we have a void print with no argument or parameter. Meaning the compiler will an ambiguous return, I believe. Okay, no, it's because of this. Because parameters with default arguments aren't counted for resolving overloaded function. Why won't the following compile? So you got a void print long x. Void print long. So you're printing a 5. Is this because... Why won't the following compile? So we're printing 5. Is it because it's an integer? Is it because it's ambiguous? Is that why? Or is it because of numeric conversion? Numeric conversion. Okay. I think I need to make a note of this. So this will not compile due to numeric conversion, as 5 is a literal int. Converting int to a long or a double is a numeric conversion, and the compiler will be unable to determine which function is a better match. Okay. So question 2. Write a function template named add that allows the user to add 2 values of the same type. The following program should run. 4, 5. Okay, so no, I don't want to save that. So we'll do include our input output stream header. We will first of all write our main function, standard character output, add, 2 and 3 to 3. So we need 2 parameters, or we need to return x plus y. So we will then do standard character output, add 1.2, 3.4. So, and then return 0. So we're going to create a template function. So we're going to do template, and we're going to do type name T, type name U. Then we're going to have a auto add, T being X and U being Y. Then we want to simply return X plus Y. And because we're using type name rather than a non-type, we don't need to use the crocodile brackets. So we run that. So we got an error. So what was wrong? That was wrong. We didn't have a semicolon. So I run it again. And we get 5 and 4.6. Nice. So for future, no, I don't want to save that. For future, nope. And then there we go. Nice. So that was good. Good to know that. So that's template functions. So now step 2 is to write a template named mult that allows the user to multiply one value of any type and first parameter and an integer second parameter. The second parameter should not be a template type. So the function should return the same type as the first parameter. The following program should run 2 times 3. Okay. So include input output stream again. So we're going to write template function here called mult. So template wait a minute. No, I did. Okay. So I think here we might need to use auto. Allow the user to multiply one value of any type. So the second type must be an integer. So does that mean we do type name t, type name u? Then if we did auto mult, with the first one being t, being x, and y, and u being y, then we return the second parameter should not be a template type. So typically we would do x times y, and then we would do that, but okay, so we've got an issue there. So typically you would do this, but I have a feeling this is where the issue will come in. Oh no, maybe auto is the correct way to do it. Oh, it is. Okay, nice. Okay, that's good to know. So, yeah, that's good to know. So that was correct. So, but is that exactly what he wanted? Okay. No, it wasn't. So that actually needs to be so that, and then this becomes int y. Okay. So in that instance, yeah, because he said the second parameter should not be a template type. Okay. Um, so step 3, I think we'll do step 3 and then we'll call it a day, and then we can do question 3 and 4. Oh no, actually we could probably finish it today. Um, Write a template named sub that will allow the user to subtract two values um, of different types. And that should actually be t. I assume then this is the instance we use auto, maybe? So include input output stream. We're writing a template type name t, type name u, t sub, and then in the body return, no, t equals x and u is y. Return x minus y. But it feels like we're just doing the same thing, and I feel int main standard character output sub 3 and 2. That's why. Sub 3.5 2. But I feel this, I think what I'm doing wrong here is because I'm not using auto, maybe that is why we will not get, I'll explain in a minute, 4 and 1.5. So let's just run that, and I assume we're going to get narrowing conversion. No. Yes, we do actually. So this means we need to convert that to that. Auto. Because you can see here we have numeric narrowing. No, okay, show errors. So, um, do we do... We did here somewhere where it instantiates both. So, but that's exactly what I'm doing here, and I'm getting an error. So undeclared identifier of sub. That's why. Because sub isn't even the name of the function. Tutto bene. Nice. So is that exactly what he wanted? Yeah, nice. Yeah, cool. So now, good that I saw that. So we'll do that, and then we'll do this. Okay, so close that. So what is the output of this program and why? So we got a template type name t. We got an integer t of count with a parameter of t. And then we got a static int of c, and we're returning plus c. So static int, static. No. No. Well, static makes it run for the whole thing. So this will be 1. This will be 2 because you're making it run throughout the whole program. This will be 3 point. This will be 3, and then this will be 2. So 1, that makes sense. 2, and the reason why this becomes 1 is because we've got a new type, which means it restarts. Remember at the beginning I had in here this, i.e. we start here with int, then we have an int, then we have a double, which means the compiler starts over again at 1, and then if we were to continue, we would then get 3 here. Okay, that does make sense actually. Okay, and I want to make a note of that. That does make sense. And the reason why it's 2 is because we've already instantiated the double. And by 2 I mean this 2 here and referring to this output. Okay, cool. What is the output of this program? We got int foo int n return n plus 10. Then we have a template type name of int foo return n. So we are calling foo of 1. So that'll just could that create unambiguous? No. This will be 11 because we no, but why using type? Um, so this will be 11 because it's referring to this, I believe. This will then be 12. This will then be 4. This will then be 2. And this will then be 16. 6. 11, correct. 2, because it's referring to this. 4, because you're creating a new instance. And what did I say? I said, I can't remember what I said. You have to go back and make sure that I'm not making it up. I can't remember what I said for this, and I said 16 for this. Okay. So in this case, foo matches to this. Makes sense. No, sorry. Foo matches to, yeah, to this. Makes sense. In the second case, does not match to this. So it matches to this. In the third case, because that's a short, because it's a short, okay. That's why that's 4, because you're creating a new instance. Instantiation. Then we have 2, because we're now creating an integer for the first time. And then we have 6, because it's not considered an int because of the empty type. Okay, cool. That makes sense. Okay, so I think we'll call it a day here. And then in the next lesson, I'm gonna go over since it's been split. No, I think I'm gonna go over constant expressions because I'm a bit stuck on that, to be honest. Yeah, yeah. I was thinking of going straight to pointers, but I think it's best if we do this, just so I get used to it. Okay, so day 25. And what did we do today? So we did function templates with multiple function template types. We did using static cast to convert arguments. Providing explicit type template argument. Function template types with multiple type template parameters. Function templates can be overloaded. Non-type template parameters and using things like autos to help defining our own ones. When they're not useful. Implicit conversions, because remember we can have implicit or explicit. Type deduction using non-type parameters using auto. Using functions in templates in multiple files. Remember, you need to do if not defined, define, and then the thing you want, and then end if. And then after if not defined and define, you use the macro processor you want. And then we did chapter 11 summary. Cool. And today's date is the 25th. And let's save that. Cool. Nice. So that's that. So next stream we'll be doing constant expressions. Actually, we've already done this. No, I'll do it. I'll do it. Okay, so that was it for today. If you've been following along, hopefully you've enjoyed C++, are enjoying it as much as I am. If you saw something I did again that I shouldn't have done, or maybe I could do something better, let me know as always. And yeah, hopefully you're enjoying it. Please like, subscribe, comment, all that good stuff. And I'll see you in the next one. Bye.